In the search for life beyond Earth, astronomers seek a specific target, a rocky, Earth-sized planet precisely distanced to support liquid water. But most stars in our universe are not like our Sun. They are red dwarfs, small, cool stars that outnumber yellow suns by a massive margin. These stars are often unstable. During their early lives, a red dwarf frequently erupts, blasting neighbors with extreme ultraviolet radiation and high-energy stellar flares. This radiation acts as a galactic wind, violently stripping the planet of its protective gases and blowing them into the vacuum. We saw this in the TRAPPIST-1 system. Despite high expectations for its 7 Earth-sized worlds, observations suggest they are likely airless, irradiated rocks. Without an atmosphere, a planet in the habitable zone remains a barren rock. On these bare worlds, liquid water would instantly boil away or freeze solid. This brings us to LHS 1140b, a planet orbiting a star 49 light-years away in the constellation Cetus. It is a tidally locked super-Earth, weighing about 5.6 times as much as our planet, orbiting a red dwarf that is uniquely quiet compared to its peers. Astronomers have confirmed that LHS 1140b has done what many thought impossible for a red dwarf planet. It has retained its air. This indicates that planetary survival against a red dwarf is possible, altering the calculation on where extraterrestrial life might exist. To prove the atmosphere exists, scientists use transmission spectroscopy. As the planet transits its star, starlight filters through the atmosphere's edge, creating distinct absorption patterns that reveal the planet's chemical makeup. In 2024, researchers using the Magellan Clay telescope in Chile detected a trail of helium escaping from the planet's upper atmosphere. Because helium is light, its presence high above the planet proved there was an atmospheric envelope thick enough to react to the star's radiation. To look deeper, astronomers used the James Webb Space Telescope. Its infrared precision allowed researchers to scan for the methane and carbon dioxide that would be found in a thick, hydrogen-rich envelope. The data showed no such signals, definitively ruling out a puffy, hydrogen-dominated sky. This finding eliminated the possibility that LHS 1140b is a mini-Neptune, the planet dominated by gas rather than rock. By stripping away these false positives, scientists were left with one scenario supported by the data: a solid, rocky planet holding a secondary atmosphere. This raises a question of physics. Why did LHS 1140b keep its air, while its sister planet, LHS 1140c, became a barren rock? Astronomers explain this through a framework called the cosmic shoreline, which predicts which planets can hold on to their volatiles. LHS 1140b's massive gravity anchors heavy molecules like nitrogen and carbon dioxide, while lighter helium escapes. Its cool orbital distance prevents the star from heating these heavy molecules to escape velocity, locking them in a stable layer. LHS 1140b survived the shoreline by being exactly heavy enough and far enough away to outlast its star's radiation. With the gaseous mini-Neptune and airless rock scenarios eliminated, the profile of this world changes. The planet's mass and radius support a remaining hypothesis. LHS 1140b could be a water world, with water making up 9 to 19% of its mass. The confirmed atmosphere provides a greenhouse effect, trapping enough heat to keep that water in a liquid state, rather than allowing it to freeze. This contrasts with our previous findings that red dwarf stars likely strip their habitable zones of the ingredients for life. LHS 1140b is now the first observationally confirmed laboratory for studying habitability around the galaxy's most common stars. If habitable conditions can survive around red dwarfs, the galaxy may be far more crowded with life-supporting worlds than we once expected.